Today we study Schrödinger equation for a charged particle. In the last class, we have derived the Hamiltonian and Lagrangian for charged particle in a relativistic formalism. For a free particle, the Hamiltonian divided by speed of light is the square root mc squared plus momentum squared. And after a long derivation, we have shown that for charged particle, Hamiltonian can be replaced by Hamiltonian subtracted by electrostatic potential, and momentum is replaced by conjugate momentum subtracted by Q over C vector potential. So after that substitution, the relativistic form for the Hamiltonian for the charged particle is expressed in this way. We'd like to find some non-relativistic expansion of this expression. To simplify this, it's better to normalize mc squared. So if I pull this mc out, then the Hamiltonian subtracted by electrostatic potential divided by mc squared is a square root 1 plus something. And if we make use of binomial expansion, the left-hand side is here. The square root is expanded 1 plus 1/2 that factor, and so on. Let us just consider the leading term. And then multiply mc squared and move this electrostatic potential to the right hand side. The Hamiltonian is a sum of rest energy and electrostatic potential plus something. So mc squared is a basic energy that is constant, and if a particle has mass, and if mass does not disappear, then it is just constant. So we had better just pull this out. And then the interaction potential is left as Q phi, electrostatic potential, and remainder. If we expand this, the second term, the first term becomes the kinetic energy, P squared over 2m. And this guy is a electrostatic potential. And then we have P dot A star, P dot A and A dot P with, there is negative sign instead of positive sign. Q divided by 2mc, P dot A plus A dot P. And then we have A squared term. That's it. Let us find a wave equation that is equivalent to these kind of expressions. Then we already know from quantum mechanics, replacement can be made by momentum is replaced by h bar over I gradient, and the Hamiltonian is replaced by IH bar time derivative. The Schrödinger equation is based on this assumption that energy of a particle is, for the free particle case, Hamiltonian is just a kinetic energy, and they are replaced by this kind of operators acted on a wave function. The free particle case, we know that wave function is minus I p dot x, the 4-vector scalar product. Okay, so wave function psi is acted by this Hamiltonian, and then right hand side is kinetic energy. That's it. What about the charged particle case? If we introduce charged particle, what we do is just replacement of the Hamiltonian and momentum by this way. We remember this guy is a Hamiltonian. That is the energy of the particle. So Hamiltonian is replaced by Hamiltonian subtracted by electrostatic potential. And this is momentum. Momentum is subtracted by the Q over C vector potential. So this is Schrödinger equation for the charged particle. let us go ahead with find some more general relation that can be extended to the relativistic case. We just want to rewrite this time derivative in terms of covariant derivative. To make this dimension the same, we multiplied speed of light, speed of light in front of it, and we pull this speed of light out. In that case, minus q phi becomes I q phi divided by h bar c. In here, it is usual to pull this h bar squared out, so we just pull out this h bar over I in front of the parenthesis. Then we have minus h bar squared 2m, open the parenthesis. For convenience, let me just put this negative sign on it, minus gradient, and then it becomes a plus I q over h bar c. Strangest thing here is that we have exactly the same kind of vector, and I have phi and a, this vector potential and the scalar potential. Scalar potential is actually the zeroth component of the full vector potential. So, why don't we redefine this complicated derivative mixed object as d0 and d vector? Then Schrödinger equation becomes I h bar c d0 phi psi minus h bar over 2m d squared psi, where d0 is this guy and d vector is this one. But we are acquainted with this contribution. That is actually the spatial derivative, covariant spatial space-time derivative of the covariant form. And the remaining piece, if we replace phi by a0, then remaining thing is just constant 4 vector. So this d0d seems to be a 4 vector object, and the first part is the usual covariant derivative, and we have additional piece that is iq over h bar c, 4 vector potential. So we call this as gauge covariant derivative. That's it.